In this video, we will add normal vectors to the arc positions. We want the normal vectors to point outwards, towards the sky. The vectors should be perpendicular to the arc edges. We will create a local function to add the normal vectors. The function will be used in the earlier function, and will have a parameter which accepts an arc. This is where we call our local function to add normals. The function does not need to return any value, since it will add the normals to the model. Inside the body of the function we will loop through the edges of the arc. To get all the edges of an arc, we use the usual expression, arc_edges. The first thing we do is get the vector along the edge. This vector will start at the first vertex of the edge, and end at the second vertex. At this point, we want to check if what we have done so far is actually working. So let's call the function we have created. Let's print the edge vectors that we create, so that we can check that it looks okay. When we execute, we can see a long list of vectors being printed. Those are all the vectors, one for each edge. We can now switch off the print. We now need to calculate the vector that is perpendicular to this edge vector. We will use some vector inline functions for this. First we will create a variable for the normal vector. To calculate the vector, we will calculate the cross product of the edge vector and a vector in the global x-axis direction. The arcs are on the y-plane. The cross product will return a vector that is perpendicular to two other vectors. In this case, we will pass in the edge vector and the x-axis vector. The result will be a vector that is pointing outwards, away from the arc. Let's print this vector, so that we can again check that we are not getting any errors. We have another long list of vectors. It looks fine. In order to help us check if the normal vectors are oriented correctly, let's visualize them. To visualize the vectors, we need to convert the vectors to rays. To do that we need to get the centroid of each edge. That will be the start of each ray. The ray can then be visualized using the visualize function. Here we can see the rays. Each ray starts at the center of the edge and points out, perpendicular to the edge and to the x-axis. Let's normalize the vectors, so they are 1 unit in length. Now we can see that the vectors are shorter. If we switch on positions, we can see that the end positions of each edge. We can switch off the visualization of the rays. What we would like to do is to calculate the normal at these end positions. The vector would have to be the average of the normals from the two adjacent edges. To do this, we will use the push attributes method. Next, we will add our normal to the edge as an attribute. The attribute will be called norm. We want to push the attribute values to the positions. We will push the attributes after all the normals for each arc have been calculated. Then each position along the arc will get the average of the two normals on either side. If we did the push inside the body of the loop, we would not get the right result. Here, we are pushing the norm attribute from edges to positions. When we execute, we will see the normals appear in the positions attribute table. Let's visualize the normals on the positions. Again, we will create a ray to do this. We can copy the previous line of code. This time, the starting points of the rays will be the XYZ coordinates of the positions. And the direction will be the norm attribute on the positions. When we execute, we can see the rays attached to the positions. Let's switch on the visualization of the previous rays as well, so that we can compare them. Now we can see both sets of rays. The rays on the edges. And the rays on the positions. You may be able to see that the direction of the rays on the positions is the average of the two edges. Now that we have normals on our positions, we can create our beams. That will be the focus of our next video.